Welcome to the deep dive. We take your sources, unpack them, and give you the essential insights. Today, we're doing a deep dive into thermodynamics.
That's right, the physics of heat.
Exactly. And it sounds maybe a bit dry, like just engines and stuff, but it actually goes way beyond that, doesn't it? It touches on everything from, like, how our bodies work to, well, the nature of time itself.
It really does. It's a huge field. And, one of the first hurdles, I think, is just the language we use every day, like heat and temperature.
Ah, yeah. People use them pretty interchangeably, don't they?
They do. But in physics, that distinction is absolutely critical. It's really where we have to start.
Okay, so temperature. That's about how fast molecules are moving, right? The average kinetic energy inside something.
Precisely. It's a measure of the state of the object, like how agitated its atoms are, on average.
So then, what's heat? How is it different? Is it about movement between things?
Exactly that. Heat isn't something an object has, it's energy that flows. It moves from a warmer thing to a cooler thing, purely because there's that temperature difference.
Right. Think about a giant iceberg. Its temperature is low, obviously it's freezing, but it contains a huge amount of thermal energy just because it's massive. It has so many molecules all jiggling just a tiny bit.
Okay, I see. So temperature is the average jiggle. Heat is the energy transfer caused by differences in that average jiggle.
You got it. And realizing heat was this transfer of energy and not some kind of invisible fluid. That was a massive breakthrough.
Yeah, that old caloric fluid idea. That heat was a substance that, soaked into things and then leaked out.
That was the dominant theory for a long time, even into the late 1700s. But then you get people like Count Rumford.
Ah, the cannon guy.
The cannon guy, exactly. He was overseeing the boring of brass cannons, drilling out the barrels.
I noticed something odd.
Very odd. The friction, just the mechanical grinding of the drill bit, was producing an incredible amount of heat.
Enough to boil water continuously.
Yeah, they used water to keep things cool, and it just kept boiling for hours, as long as the drilling continued. So if heat was this caloric fluid inside the metal,
then the metal should have eventually run out of it, right? But it didn't. The boiling just kept going as long as the work was being done.
Ah, so the heat wasn't in the cannon to begin with.
Exactly. Rumford realized the mechanical energy, the orderly motion of the drill, was being transformed into this disorderly energy we call heat. It was a conversion.
And that understanding that heat is energy, that energy changes form, that's the bedrock for the laws of thermodynamics, isn't it?
Absolutely. It paved a way. So let's maybe start with those fundamental rules. The zeroth and first laws.
Okay. The zeroth law, it always sounds a bit basic.
It does, but it's foundational for understanding the flow. It just says heat naturally flows from a hotter object to a colder object.
Until they reach the same temperature, thermal equilibrium.
Right. Put your hot coffee next to your cold water. Eventually, they both end up lukewarm. That's the zeroth law in action. Simple, but crucial.
Okay, so that sets the direction of natural flow. Then the first law. That's the big one about energy itself, isn't it?
That's the law of conservation of energy. The bookkeeper, you could say.
Energy can't be created or destroyed, only transformed.
Precisely. It tells us how to account for energy changes. If you look at any system, the change in its internal energy equals the heat flowing in minus any work the system does on its surroundings.
So it's like, you can't get more energy out than you put in. You can't win.
You can't win, exactly. You can really only hope to break even in terms of total energy.
But often, you don't even break even in terms of useful energy because some gets degraded.
That's a key point. The first law still holds even when the conversion is messy, like friction, back to Rumford.
Right.
You use ordered mechanical energy to push something, but friction immediately turns some of that into disordered heat. The total energy is the same, but the heat is often less useful for doing work.
Got it. So energy is conserved, but its quality can change.
Exactly.
And this whole energy flow thing, it applies on a massive scale, too. You mentioned water earlier. Our sources highlighted its heat capacity.
Ah, yes. Water is remarkable. It has an incredibly high specific heat capacity.
Meaning it takes a lot of energy to raise its temperature.
A lot. It can soak up huge amounts of heat without getting drastically hotter itself. It's like a giant thermal buffer.
And this isn't just a lab curiosity, right? It drives weather.
Absolutely. It explains things like sea breezes. The land heats up faster than the sea, creating a temperature difference, driving wind.
Okay.
But also huge climate patterns. Think El Nino. That's all about vast amounts of heat stored and moved around in the Pacific Ocean, affecting weather globally, all thanks to water's high heat capacity.
Wow. So the basic physics of heat capacity has these massive planetary consequences.
It really does.
Okay, so zeroth law sets the direction. First law handles the accounting. Energy is conserved. But neither of those laws says you can't build a perfect machine, right? A 100% efficient engine.
Correct. They don't forbid it. That's where the second law comes in. And this is where reality starts to bite for engineers.
Law of limits.
The law of limits, exactly. It tells us what we can't do. And we see it immediately with things like refrigerators and air conditioners.
Because they're fighting the natural flow. They're making cold things colder and hot things hotter, pushing heat the wrong way.
They're pushing heat uphill against the zeroth law's natural direction, from the cold inside to the warmer outside.
Which is why they need power, right? You have to plug them in.
You have to put energy in, usually electrical energy, to force that heat transfer against the natural gradient.
It reminds me of that old thing about trying to cool your kitchen by leaving the fridge door open.
Ah, yes, the classic example. It doesn't work, does it?
No, because the fridge motor and coils at the back are actually dumping more heat into the room than the cold air coming out of the front.
Exactly. The work done to move the heat generates its own waste heat, making the room warmer overall. You're paying electricity to heat your kitchen.
Okay, so that's the challenge of moving heat uphill. What about the other way? Using heat flowing downhill to do work, like steam engines, car engines.
Heat engines, yes. They take heat from a hot source, convert some of it into useful work, and dump the rest into a colder environment.
Okay, let's unpack this. This is where engineers in the 1800s hit a wall, wasn't it? They couldn't get perfect efficiency.
They couldn't. No matter how clever their designs, some heat was always wasted, expelled as exhaust.
It wasn't just bad engineering.
No, it turned out to be fundamental. This is where Sadi Carnot, the French engineer, comes in. He figured out the theoretical maximum possible efficiency for any heat engine.
The Carnot limit.
The Carnot limit. And what's fascinating here is it doesn't depend on the engine's specific design. Not really. It depends only on two temperatures.
The temperature of the hot source, where the heat comes from.
Like the burning fuel, call that dollars for hot.
And the temperature of the cold sink, where the waste heat gets dumped. Like the outside air for a car engine, call it dollars for low.
Exactly. And the maximum possible efficiency is given by the formula. Efficiency equals 1 minus BLers divided by dollars.
But crucially, those temperatures have to be in an absolute scale, right? Like Kelvin, where 0 is really zero energy.
Yes, that's vital. Because think about the formula. If you could somehow make the cold sink temperature $2 equal to absolute 0.
Then $2 would be 0, and the efficiency would be 1 minus 0, which is 1 lower, or 100%.
The perfect efficiency, but you can't reach absolute 0 in reality.
Right. Physically impossible.
Yeah.
So $2 is always greater than 0.
Which means $2 is always some positive number, however small.
And 1 minus that positive number is always less than 1.
Always less than 100% efficiency. Some heat must be wasted. It's not a design flaw. It's baked into the physics of heat flow between two temperatures.
Wow. Okay, so the universe essentially demands a waste heat tax on any attempt to turn heat into work.
That's a great way to put it. And this unavoidable waste, this is what leads us to the deepest concept in thermodynamics. Entropy.
Right. So why? Why does physics demand this tax? If energy is conserved, first law, why can't we just use it all? Why the waste?
Because fundamentally the universe tends towards, well, messiness, disorder.
And that's entropy, a measure of disorder.
That's the concept, yes. Entropy is a measure of the disorganization or randomness or the number of ways a system can be arranged.
Okay. Examples.
Think of a deck of cards. Perfectly ordered, new deck order that's low entropy, very specific state, shuffle it.
It gets messy.
Random.
Exactly.
There are vastly more ways for the cards to be disordered than ordered, so shuffling overwhelmingly leads to a higher entropy state. Or imagine spraying perfume in one corner of a room.
The smell spreads out.
Right. The molecules diffuse randomly until they're spread uniformly throughout the room. That's a much more disordered, higher entropy state than having them all concentrated in the corner. They don't spontaneously go back into the corner.
Okay. Things tend to spread out, become more random.
That's the essence of the second law in its most general form. It states that for any isolated system, anything cut off from energy exchange with the outside, the total entropy will never decrease.
It either stays the same for idealized reversible processes, or much more likely, it increases.
Right. Disorder tends to increase, always. For the universe as a whole, which is the ultimate isolated system, entropy is always going up.
Here's where it gets really interesting, because this connects to time itself, doesn't it?
It absolutely does. Think about most other physics laws like gravity. Newton's laws work the same forwards or backwards in time. A planet orbiting a star. If you filmed it and ran the movie backward, it would still look perfectly plausible according to the laws of gravity.
Right, the physics doesn't care about the direction of time.
But the second law does. The relentless increase of entropy gives time its arrow.
Ah, because we never see the reverse happen spontaneously.
Exactly. You never see a shattered glass spontaneously reassemble itself. You never see the perfume molecules rush back into the nozzle. You never see a crumpled car suddenly straighten itself out on the side of the road.
Watching that movie in reverse looks wrong.
It looks wrong because it violates this incredibly powerful statistical tendency towards increasing disorder. The universe moving from less probable ordered states to more probable disordered states is what defines the forward flow of time for us.
So the arrow of time is the arrow of increasing entropy.
That's the profound connection.
Okay, let's tie this back to the engine. Carnot's limit, the wasted heat. That's the entropy tax.
That's the entropy tax. To get useful, ordered work out of disordered heat energy, you must increase the overall entropy of the universe. You do that by dumping some of that energy as even more disordered waste heat into the cold sink.
So the engine creates order, work, locally, but only by creating even more disorder, waste heat, globally. The net result is always more disorder overall.
Precisely. The universe gets its payment. And this whole principle still drives engineering today, right? Trying to make engines more efficient.
Absolutely, like designing jet engines. A huge part of improving their efficiency is finding materials that let them run hotter.
Increasing $, the hot temperature in Carnot's formula.
Right. The hotter you can run the combustion, the bigger the potential efficiency. Even though you still have to dump waste heat, you're just trying to minimize the fraction that's wasted within that fundamental limit.
Pushing closer to the Carnot limit for the temperatures involved.
Okay, so if entropy is always increasing for the universe, where does that ultimately lead?
Well, that leads to the rather grim long-term forecast known as the heat death of the universe.
Heat death. Sounds ominous.
It's the theoretical end state. If the universe keeps expanding and entropy keeps increasing, eventually everything reaches a state of maximum disorder. All energy becomes uniformly spread out.
Meaning no temperature differences anywhere.
Exactly. Everything at the same very low uniform temperature. And if there are no temperature differences,
Then ballers equals $10. The Carnot efficiency becomes zero.
no more temperature gradients to drive heat flow, no more possibility of extracting useful work from heat. Everything just sits there in a state of maximum entropy, thermal equilibrium. The universe essentially runs down.
Wow. A universe that's run out of steam, literally. Okay, that's a big thought. Let's end with maybe one more puzzle, something closer to home, but still tied to all this.
This raises an important question. If the universe always tends towards disorder, how did we get life?
Right, life is incredibly ordered. Complex structures, intricate processes. It looks like a massive decrease in entropy locally. How does that happen?
It seems like a paradox, doesn't it? A blatant violation of the second law.
But it can't be, otherwise the law isn't universal.
It isn't a violation because a living organism is not an isolated system.
It needs energy from outside. Food, sunlight.
Exactly. Life takes in high-quality, low-entropy energy, like sunlight or chemical energy in food, uses it to build and maintain its own complex, low-entropy structure.
In the process.
It dumps vast amounts of low-quality, high-entropy waste heat and simpler waste products back into the environment. Think about the heat your body gives off right now.
So the organism decreases its own entropy, creates order within itself.
But only by increasing the entropy of its surroundings by an even larger amount. The net entropy change for the organism plus its environment is still positive.
Life creates local order by accelerating the universe's overall slide into disorder.
That's the thermodynamic view, yes. Life is a remarkable temporary eddy of complexity in a universe that's constantly trying to smooth everything out.
That's incredible. So the ultimate question isn't if life violates the second law. It doesn't. But how those initial steps happened. How did non-living matter first harness energy to start building that low-entropy complexity while still paying the entropy tax?
Precisely. That transition from non-life to life, powered by external energy sources like the early sun or geothermal vents, while obeying the laws of thermodynamics. That's one of the deepest scientific mysteries we're still trying to fully unravel. It's all tied up in these fundamental laws of heat and disorder.